In the previous video, we learned about the first and second derivative tests as the ways that we will classify critical values as either local minima, local maxima, or neither local minima nor local maxima. Points that kind of look like the bottom of a valley versus points that look like a mountaintop versus points that are neither the bottom of a valley nor a mountaintop. We talked a lot about the theory behind stuff, but I didn't really give you a good example, so that's what I want to do in this video. I want to work through a couple examples of varying degrees of difficulty and introduce a few new vocabularies as I do so. So the first example I want to look at is a polynomial. F of x equals 2x cubed minus 9x squared minus 24x plus 5. The graph is pictured here, but I want to do all of our analysis without this graph. This is just pictured to try to help you visualize what's going on. We want to figure out where this graph has a relative or local maximum and a relative or local minimum. With the graph, it's easy enough to locate them. Looks like my local max is somewhere up here, my local min is somewhere down here. But again, we're pretending we don't have the graph, so we're going to try to do this whole thing algebraically. The way we do it algebraically is we'd first look for critical values. To find critical values, we take the first derivative and set it equal to 0. The first derivative is easy enough to figure out because it's just a polynomial. The derivative of 2x cubed minus 9x squared minus 24x plus 5 is 6x squared minus 18x minus 24. Now that I have the first derivative, I can find critical values by taking that first derivative and setting it equal to 0. In other words, solving the equation 6x squared minus 18x minus 24 equals 0. You might notice that all three of these terms on the left have coefficients that are a multiple of 6. So I can divide both sides of the equation by 6, and I get x squared minus 3x minus 4 equals 0. This equation looks a lot easier to solve. I think I could solve it by factoring. Factoring the left-hand side of this equation gives me x minus 4 times x plus 1. I have a product of two things equaling 0. That means either x minus 4 equals 0 or x plus 1 equals 0. In other words, either x equals 4 or x equals negative 1. The first derivative equals 0 when x equals 4 or x equals negative 1. What that means is this function has critical values at 4 and negative 1. If I were to draw tangent lines to this curve when x equals 4 and when x equals negative 1, I would see that those tangent lines are horizontal. Yeah, cool. That's what we learned in the previous section. In this section, we're not just supposed to find our critical values. We're supposed to classify them as either relative maxima or relative minima. Well, we have two options in terms of how we do that. Either we can use the first derivative test or the second derivative test. I think what you'll see as you get better at these is you're going to prefer the second derivative test. So that's what I'm going to demonstrate. To use the second derivative test, not surprisingly, you need to know the second derivative. Fortunately, the second derivative is just the derivative of the derivative. And since the derivative is just a polynomial, the second derivative is pretty easy to figure out. The derivative of 6x squared minus 18x minus 24 would be 12x minus 18. It's tempting to take this thing and set it equal to 0 and solve because that's kind of what we did over here, but that's not what we want to do. We don't want to know when the second derivative equals 0. That would give us the inflection points, which is interesting and all, but not what we're looking for here. What we want to know is, at these different critical values, would the second derivative be negative or positive? To classify the critical value at x equals 4, what we want to do is consider f double prime of 4. F double prime of 4 is just what comes out of this machine when we put 4s into it. 12 times 4 minus 18. You can actually compute that value if you want. 30, I think it ends up being. But really, you don't have to. All you have to realize is that it gives you a value that's greater than 0. At the point where x equals 4, this function is concave up. When my function is concave up, it has a shape that kind of looks like this. If it's a critical value at a point where it's concave up, I've got a local minimum. It should be the case that at x equals 4, my graph has a local minimum. Oh yeah, sure enough it does. Here's the point right here. Here's the shape, this concave up shape that I figured out when I evaluated the second derivative at 4. I can do the same thing to classify the critical value at x equals negative 1. I just take my second derivative, change all the x's into negative 1s, so I get 12 times negative 1 minus 18. You can figure out what that is if you want, negative 30 I think, but again, it doesn't matter. All that matters is that it's less than 0. The fact that it's less than 0 means the graph is concave down at that point, so it has this shape. If we're talking about a critical value, when the graph is concave down, we're talking about a local maximum. It should be the case that at x equals negative 1, my graph has a local maximum. Sure enough, it does. This function has a local or relative maximum at x equals negative 1, and it has a local or relative minimum at x equals positive 4. You might note that in this specific question, we didn't just want to know where the local or relative maximum and minimums were. We wanted to know what the local, relative, and maximum minimums are. In other words, what is the value of the function at these points? Often you just need to know the x-coordinate, but sometimes you'll run into problems where we also want to know the y-coordinate. To figure out the y-coordinate, it's easy enough. All you're doing are taking these x-coordinates and plugging them back into the function. It's simple, but it's easy to overcomplicate things because we've calculated the first derivative and the second derivative, and we've plugged numbers into the second derivative, and it might be tempting to take the -1 and plug it in, I don't know, over here or something. But you don't want to do any of that. All this is asking is, what is the value of the function at this relative maximum where x equals -1? To figure that out, I evaluate f of -1, which is 2 times -1 cubed, minus 9 times -1 squared, minus 24 times -1 plus 5, which is what, -2, and then positive 1 times -9 is -9, -24 times -1 is positive 24 plus 5. I got 29 on the positive side, and I got -11 on the negative side. Sounds like I got 18. When x equals -1, the function should have a height of 18. Yeah, that looks about right. The height of this point appears to be right around 18. The value of my relative maximum is 18. Similarly, I can figure out the value of the relative minimum by just taking x equals 4 and plugging that into this function. I don't really want to do that. If I do it, I think I'll get some number that's about -108. I guess I should do it. I just don't want to. 2 times 4 cubed minus 9 times 4 squared minus 24 times 4 plus 5. Let's see, 4 cubed is the same as 2 to the 6th, which is 64, and 64 times 2 I think is 128. 4 squared is 16, and 16 times -9 is almost 16 times -10, which is -160. But I'm 116 short of that, so I guess I'm -144. 24 times 4 is almost 25 times 4, which would be 100, but it's 4 short of that, so it's 96. I get -96 here, and then I get a plus 5. These numbers feel familiar. I might have already done this in some other example. Anyways, I got 128 and I have 5, so I have 133 on the positive side, and I got -144 and -96, so I have -240 on the negative side. Oh, I was so close. It looks like I get -107 here, not the -108 that I predicted. Anyways, the point is just, typically you're done at this stage, which is what we figure out using the second derivative test. But once in a while, you'll be asked to evaluate the y-coordinates also, and now you know how to do that. It's worth pointing out that I used the second derivative test here, but I didn't have to. I could have also used the first derivative test. If I were using the first derivative test, what I would do is recognize that the first derivative is only going to change signs at these critical values here. I have 2 critical values, so that divides my number line up into 3 different regions, maybe region 1, 2, and 3. I take any number I want in region 1 and I test it. What do you mean test it? Take any value you want from region 1, I don't know, -5 for example, and throw it into the first derivative. Evaluate f prime of maybe -5. If you do that, what you'll see is you get a positive number. What that means is my first derivative is positive over here in region 1. Do the same thing for region 2. Pick any number you want. Maybe you'd pick 0 and evaluate the first derivative at 0. If you do that, what you'll find is you get a negative number. So the first derivative is negative in region 2, and thus the graph is decreasing as we see pictured here. At this critical value, my first derivative switches from positive to negative. Therefore, the first derivative test tells me that this critical value must be a local maximum. Similarly, if we test a number in region 3, I don't know, 6 maybe, if we figure out f prime of 6, what we'll see is we get a positive number. That means my first derivative is positive. That means at this critical value, my first derivative is changing from negative to positive. Therefore, I must have a local minimum as specified with my first derivative test right here. It works. It's totally fine to use the first derivative test. It's just a little bit tedious to do this extra step where you pick these numbers and test them. So most students prefer to get these answers using the second derivative test, which is what I originally depicted. One more example. It's a harder example. It's harder if you just look at the graph, and it's harder when you look at things algebraically. I think what you'll find are we have 2 different critical values here. One of them is fairly obvious. It's some number up here that appears to be pretty close to -1. But there's another one, And it's hard to see where it is, but I think it's roughly somewhere in here. I don't know exactly where it is. I can't tell from the graph, but maybe if you look really closely, you'll see if you were dumping water in here, there'd be some point where a little puddle would form, right? It's a little bit higher over here than it is here, and it's a little bit higher over here than it is here. Somewhere near 4, I think, we're going to see that we have a local minimum. We definitely have a local max over here, and I claim we have a local min somewhere over here. Don't believe me? Well, we could figure it out algebraically. We know f of x, so we can calculate f prime of x. To figure out f prime of x, we take the derivative of this mess. Maybe you're at the point where you can look at this and see two different terms. The first term is just the 7. The derivative of that 7 is going to end up being a 0. The second term is x squared minus x minus 5 times e to the negative x power. When I take the derivative of that term, I'm going to end up using the product rule. So from this term I get a 0. From that I want to subtract. Using the product rule, I have to take the derivative of the first thing, the x squared minus x minus 5, and then multiply that by the second thing, the e to the negative x. And then to that I want to add the derivative of the second thing, so the derivative of e to the negative x power, times the first thing left completely alone, x squared minus x minus 5. I don't even need to write this 0. I got negative, whatever the derivative of x squared minus x minus 5 is. Maybe you can just look at that and tell that it's 2x minus 1 times e to the negative x left completely alone, plus the derivative of e to the negative x. You might have to use a chain rule in here, or maybe you can just see that that derivative will be negative e to the negative x times x squared minus x minus 5. We're all done with the d over dx symbols, so we're done with the calculus part of figuring out f prime of x, but we might want to clean this up a little bit. We could take the negative and distribute it through both terms. That would make this term negative and make this term positive. And then we could factor out e to the negative x from both terms, and what that would give us is e to the negative x times the negative of 2x minus 1 plus x squared minus x minus 5. A little bit of tricky algebra there, but I think if you go slowly, you can convince yourself that these two lines are equivalent. I'm just about done, but I want to take this one step further. I want to get rid of the parentheses inside these parentheses. These parentheses aren't doing anything at all, so I can just drop them. But these parentheses have to take the negative 1 and distribute it through. So I get negative 2x plus 1 plus x squared minus x minus 5. As long as I've gone this far, I might as well combine like terms. I just have the single x squared here, but if I look at my x terms, I got negative 2 here and negative 1 here. So I got negative 3x, and then I have the plus 1 and the minus 5, so I get negative 4. F prime of x in its cleanest possible fashion is e to the negative x times x squared minus 3x minus 4. Now that we have the first derivative, we can figure out our critical values by taking that first derivative and setting it equal to 0. I don't know, maybe over here. So I got to figure out when e to the negative x times x squared minus 3x minus 4 is equal to 0. It's something times something, so the only way it equals 0 is if that first something, e to the negative x equals 0, or that second something, x squared minus 3x minus 4 equals 0. It's not obvious, but this doesn't have any solutions. One way you could convince yourself of that is that e to the negative x is 1 divided by e to the x power, and the only way a fraction can equal 0 is if the top equals 0. And the top never changes, it's just the number 1, so this whole thing's never going to be equal to 0. If the bottom were equal to 0, well, then the first derivative would be undefined, and it turns out that's important also, but it turns out we don't have to worry about that either, because the bottom can never equal 0, because there's no number you can raise e up to make it equal to 0. You're like, what about 0? Nah, e to the 0 power is equal to 1. What I'm trying to say is not only are there no solutions to this equation, there's not even any ways we could make e to the x equal to 0, in which case we'd get an undefined first derivative, which technically also yields a critical value. There we go, I know I wrote that somewhere. Critical values when f prime of x equals 0, and technically also when f prime of x is undefined, but I told you that's not really going to happen in our class. You don't have to worry a whole lot about that. Anyways, the point is there's no solutions over here, so any solutions to this equation are going to come when x squared minus 3x minus 4 equals 0, and the nice thing about x squared minus 3x minus 4 is I made these numbers up myself, so it's going to work out really nicely. It's going to factor to x minus 4 times x plus 1 equals 0, so either x is equal to 4 or x is equal to negative 1. Wait, what were we doing again? Remember, we took the first derivative and set it equal to 0 to figure out critical values. The reason we figured out critical values is because critical values come in 3 flavors: relative minimum, relative maximum, and neither. We want to know relative minimum and relative maximum of this graph, so we kind of have these two candidates, 4 and negative 1. If we go back up to our graph, which we're pretending we don't have, We know that the critical value at -1 is going to end up being a local max, and sure enough, there is a critical value at 4, as we kind of guessed earlier, and that's going to end up being our local minimum. But again, we're pretending we don't have the graph, so at this point, all we know is we have these two critical values, and it's up to us to determine whether they're relative minima or relative maxima. To do that, we got two options. We can either classify with the first derivative test or the second derivative test. I'm partial to the second derivative test, so that's what I'm going to do. If I'm going to use the second derivative test, well, I got to know the second derivative. Second derivative is just the derivative of the derivative, so I can pick any form of the derivative, I guess any of these lines here. I kind of like this bottom one, and take the derivative of that. So I need the derivative of e to the negative x times x squared minus 3x minus 4. It's something times something, so when I'm taking the derivative, I'm using the product rule. Product rule tells me take the derivative of the first thing, e to the negative x, multiply that by the second thing, x squared minus 3x minus 4, and add to that, how many times do you think I've said this in this class? The derivative of the second thing, x squared minus 3x minus 4, times the first thing, e to the negative x power. Got two derivatives to take in this line, the derivative e to the negative x, which is negative e to the negative x. Use the chain rule here if you need. Then multiply that by x squared minus 3x minus 4. Then add to that the derivative of x squared minus 3x minus 4. Polynomial derivatives are easy. It's just 2x minus 3 multiplied by e to the negative x power. You could leave things like this, but what I'm going to do is factor out, I don't know, maybe negative e to the negative x. And if I do that, I'm left with x squared minus 3x minus 4 from this first term. And from this term, the e to the negative x is gone. And I've pulled out a negative, which makes this positive and negative. And if I take that negative and distribute it through, I get negative 2x plus 3. I can combine like terms to write my second derivative as negative e to the negative x times x squared minus 5x minus 1. Now that I know the second derivative, I can classify my critical values. Maybe first I'll classify x equals 4 by evaluating f double prime of 4. That's going to be negative e to the negative 4th power times 4 squared minus 5 times 4 minus 1. As I think I've mentioned a few times, we don't really care about the value of this thing. We just care whether it's negative or positive. If we look at the stuff inside the parentheses, we got 16 minus 20 minus 1. So that's definitely going to be negative. I don't know what number it is, but it's definitely going to be negative. If I look at this first term, e to the negative 4th power is the same as 1 over e to the 4th power. E is a positive number. When I raise it to the 4th power, it's still positive. So I have 1 over a positive number, which is still positive, but I'm taking the negative of that positive number. What I'm saying is negative e to the negative 4th is also a negative number, and a negative number times a negative number is a positive number. I don't know what number it is. I don't care what number it is. The second derivative is positive at this critical value of 4. Therefore, 4 is a local minimum. Wait, local minimum? Why is it a local minimum? Because if the second derivative is positive, you're thinking concave up, so it kind of has this shape, and the critical value is the flat part of this bowl, which is definitely a local minimum. If you look really carefully, you'll see this shape right here. It's just a super shallow bowl. Couldn't get a whole lot of liquid in there, but a bowl nonetheless. I already know what's going to happen when I classify this other critical value, x equals -1, because I have the graph, but we might as well go through the steps. F double prime of -1. Remembering that my second derivative is negative e to the negative x times x squared minus 5x minus 1. The second derivative evaluated at -1 would be the negative of e raised up to the negative -1, in other words, the first power, times -1 squared minus 5 times -1 minus 1. -1 squared is +1. -5 times -1 is +5. So I got 1 plus 5 minus 1. These parentheses evaluate to a positive number. Negative e to the first power is a negative number because e to the first power is just e, and e is positive, and the negative of positive is a negative. I got a negative times a positive. I got a negative number. Since my second derivative is negative at this critical value, I know that I have a local maximum here at x equals -1. Yes, we already knew that just by looking at the graph. However, this whole exercise was supposed to assume that we didn't have the graph, so we wanted to do things purely algebraically. All this work that I did here in these various colors was really just to answer this first question. I haven't even gotten to the second question. And the second question is what I want to end this video with. In the second question, we're not looking for relative or local minimums and maximums. We're looking for absolute or global minimums and maximums. In this case, we're just asked about the maximum, but there's no reason you couldn't ask about the minimum either. The point that I'm trying to make here is we can put another adjective in front of the word minimum or maximum. Instead of that adjective being local or relative, we can use the adjective global or absolute. In order to be the absolute maximum, not only do you have to be higher than all the rest of your neighbors, you have to be higher than any point on the graph. Just by looking at this, we can tell that this point at x equals -1 is a local maximum and a global or absolute maximum. But if we didn't have the graph, that analysis would be a little bit harder. What we'd have to do to figure out global maximums is consider any local maximums and also the end behavior. In this case, as the graph goes to the left, the height goes towards -infinity. So I'm not going to have any global maximums over on this side. And when I go to the right, the height looks like it approaches 7 asymptotically. So since this local max had a height of 15, which is greater than the 7 end behavior on this side and the -infinity end behavior on this side, the local max is also a global max. Note that we didn't know this local max had a height of 15 from the analysis that we did down here. The way we'd figure that out is doing analysis similar to what we did in the previous video, where we not only figured out the x coordinate of the local max, but we also figured out the corresponding y coordinate.